Group 1 members are lithium, sodium, potassium, rubidium, cesium, and francium. Group 1 elements are metals, called alkali metals. The abundance, normalized to 1 million silicon atoms, of the Group 1 elements on Earth is shown here. Sodium and potassium are very abundant on Earth. The typical physical properties of the alkali metal, Group 1 metals, and their ions are summarized in the table. You may notice that there is only one valence electron for each element. The atomic radius increases with the atomic number. So does the ionic radius. The electronegativity values of Group 1 elements are almost the same. The first ionization energy, IE1, decreases down the group, so does IE2. IE2 is much larger than IE1, indicates the difficulty to remove one more electron from a monocation. The atomization energy decreases down the group, indicates the interaction between atoms decreases. The principal visible emission lines are the colors we see in the flame test. The color we named depends on the emission and the sensitivity of our eyes. Lithium, carmine; sodium, yellow; potassium, violet; rubidium, bluish red; cesium, blue. Question. Let's look back to the ionic radii of sodium ion and potassium ion. What will the 33 picometers difference make? Question A. Did you have heard of Gorilla Glass? And B. How is it made? Gorilla Glass is a brand of toughened glass developed by Corning Corporation. It's well known for its use as a substrate touch panel display in mobile phone. Such a toughened glass was experimented in 1960, but revived in 2005 due to the invention of iPhone by Apple Corporation. The glass is toughened by ion exchange during its manufacture. The glass is immersed in a molten alkaline potassium salt at around 400 degrees C, wherein small sodium ions in the glass are replaced by larger potassium ions. The larger ions occupy more volume and thereby introduce a surface layer of high residue compressive stress at the surface, which gives the glass increased strength and toughness. There is only 36 angstrom difference between the sodium ion and potassium ion. Size matters. Considering the electronic configuration and the fact that there is only one valence electron for each Group 1 element, we can expect the easy loss of the electron and the high chemical reactivity of the alkali metals. See the chemical reactions of lithium for reference. Lithium reacts with ammonia, water, nitrogen, halogen, hydrogen, etc. Group 1 metals are highly reactive. Question. We already knew, even in your high school course, that alkali metals are reactive. For example, potassium reacts with water very violently. Do you know what is the mechanism of the reactions? Why the reactions are so violent? The answers are: number one, heat. Lots of heat generated in the reaction leads to the explosion or boiling of water. Number 2, hydrogen explosion. Hydrogen gas produced in the reaction is ignited by heat, then exploded. Number 3, Coulomb explosion. As matter reacts with water, the valence electron is lost so quickly that metal or metal surface has excessive positive charges. The charges repel each other and then explosion takes place. The enthalpies of formation and the lattice energy of alkali metal halides are summarized in the table. From the table we notice for fluorides, values of the enthalpy of formation become less negative down the group. What? For chlorides, bromides, and iodides, the reverse trend is true. For a given metal, the enthalpy of formation of the halide becomes less negative. See the value from left to right in each row. As the halide ion size increase, the value of enthalpy of formation and the lattice energy decrease significantly. The high lattice energy of lithium fluoride is believed to be responsible for the poor solubility in water. But the solubility of other halides is much complicated to be understood. Group 1 metal react with oxygen, give oxides, peroxides, superoxides, etc., under different reaction conditions. In suboxides, the formula is a bit misleading in terms of oxidation state. It's suggested to add electrons to show the presence of free electrons in the suboxides clusters. Here you see 5 electrons. Lewis' structure of oxide, peroxide, and superoxide ions are shown at the bottom. All the group 1 peroxides decompose on heating. All the alkali metal oxides, peroxides, and superoxides react with water, and all the carbonates are not thermostable. It's found that the solid-state structures of sodium bicarbonates and potassium carbonate exhibit hydrogen bondings. In potassium carbonate, the anions are associated in pairs, while in sodium bicarbonate, polymeric chains are present. Alkali metal ions are positively charged, will attract negatively charged species. Oxygen atoms in polyether, like a crown ether shown here, is actually electron-rich. The electrostatic interaction between the metal ions and the oxygen gives the complex ions, as shown on the slide here. A concept of matching ligand hole size to the size of metal ions plays a key role in discussions of the apparent selectivity of particular ligands for particular metal ions. The stability constant for complex ions is K plus larger than rubidium plus larger than cesium plus, nearly equal to sodium plus and larger than lithium plus.